Hi, I'm Renjie Li from the Institute of Software, Chinese Academy of Sciences. It's my pleasure to share our recent work on neural network robustness analysis. The paper title is Towards Practical Robustness Analysis for DNNs based on PAC-Model learning, and we named the method DPAC. This is a joint work with Peng Feiyang, Chen Chaohuang, Youchen Sun, Bai Xue, and Li Junzhang. Robustness is a property that shows the ability to resist change under perturbation. When we talk about the robustness of a deep neural network, DNN for short, we want to study the output of the DNN in the neighborhood of the inputs. In this paper, we analyze the local robustness regarding a single input. A critical measure is the maximum robustness radius, where a DNN can hold its robustness. The problem here is to estimate it. Before introducing our method, we review several existing methods to estimate the maximum robustness radius. The first one is the constraint-solving-based verification. It encodes the problem into an SMT problem or a MILP problem, and the exact maximum robustness radius can be derived. However, the efficiency is poor due to the splits on the uncertain neurons, and it can only adapt to simple and small networks. The second approach is the abstract interpretation-based verification. Compared with the previous technique, it reduces the computational cost by using the abstract domains to over-approximate the uncertain nodes. However, since the error introduced by over-approximation accumulates, the estimation given by this method could be very conservative. The third approach is the adversarial attack, which tries to prompt a counterexample that violates the robustness property. White box attacks are often gradient-based and thus very efficient. However, there is no guarantee on its estimation of maximum robustness radius. The final one is the statistical method. It utilizes hypothesis testing from statistics by considering whether the property holds or not as a random variable. It can give a probabilistic guarantee on its estimation. Nonetheless, it cannot reflect the robustness effectively because of the huge input space. We will later show that the statistical approach is the most inaccurate estimation. We can conclude a trade-off between the accuracy and the efficiency from the existing methods. The verification methods take care of the details of the entire network, while the statistical approach treats the network as a black box. The key challenge here is to achieve a good balance of the trade-off. How to efficiently analyze the robustness with a guarantee. Here, we solve this dilemma from the perspective of model learning. Imagine a surrogate model which is extremely similar to the original DNN. If we can verify the robustness of the surrogate model, we may transfer the property to the original DNN. So the main idea of our paper is to learn a good enough model and then analyze the robustness of the learned model. Since we want to estimate the robustness with some guarantee, we must define the meaning of the good enough. Here, we bridge the learned model with the original DNN by a probably approximately correct, PAC for short, guarantee. The absolute error between the learned model and the original model is bounded by lambda, with the confidence at least 1 minus eta and the error rate epsilon. What we learn here is the score difference function of the original DNN. The score difference function is a good indicator of the robustness. As the score difference is smaller than 0, the model is robust, so we will learn its surrogate under the PAC guarantee. There are two phases in the workflow of our framework. First, we implement scenario optimization to learn a linear model with a PAC guarantee. Scenario optimization is a method to solve the robust optimization problem, which has infinite constraints. It samples the constraints and only considers the finite subset of the constraints. If the number of the samples is larger than a given threshold, the solution satisfies all the constraints, but only at most a fraction of probability epsilon, with confidence at least 1 minus eta. The m in the threshold is the dimension of the optimization variable c. In our implementation, we bound the absolute error between the learned model and the original model as constraints, and encode the problem as linear programming. After solving the linear programming problem, we get the surrogate model with a PAC guarantee. We call the surrogate model as a PAC-Model for the original DNN. So we say the original model is PAC-Model robust if the surrogate model plus the margin lambda is smaller than 0. We illustrate this by a simple example. Here, the blue dashed line is a PAC surrogate of the black piecewise linear model. We check if the upper bound is smaller than 0 or not to verify the PAC-Model robustness. Since we learned a linear model, so the maximum point can be easily derived, and the property can be verified instantly. We also introduce some optimizations to boost the scalability of our framework. In our framework, we try to use the scenario optimization technique to learn the score difference of the original DNN. The number of the constraints needed to achieve the PAC guarantee is linearly increased with the number of optimization variables. Since the classification task often contains multiple objects, the dimension of DNN's output can be really high. It will need more variables and constraints to build the LP problem that is too large to solve. To reduce the number of variables and constraints, we decided to compute the PAC model for each component separately. It will break the large LP problem into many smaller problems. After solving all the smaller LPs, we recalculate the overall lambda considering all the learned components together. This will make our framework more scalable to high output dimension tasks. For extreme cases like ImageNet, which has over 1,000 classes, we use an on-target variant of the score difference function. It reduces the problem into one smaller LP problem at the expense of linearity. Besides, considering the high dimension inputs like images, we propose several optimizations. Inspired by explanation work like GridCam, we notice that the object-sensitive pixels are more important than other pixels. So we learn a coarse model by linear regression before the linear programming. We identify the important pixels and then refine the model with only these pixels. This focused learning will significantly reduce the computational cost, but with little precision loss. When the dimension of this input further scales, We extend the one-step focused learning to the multi-step one called stepwise splitting. The stepwise splitting will split the image into grids and run a coarse model on these grids to identify the significant ones. The significant grids will be further split and refined. Here, we'll illustrate the stepwise splitting with a golf ball image. One can see with the fineness of the grids evolved. The significant features are extracted and refined iteratively. Now we show some of the experimental results in our paper. We first evaluate the 4 methods on 12 networks on MNIST. In most cases, Provero ends up with a maximum robustness radius over 100, which is even larger than the upper bound identified by PGD. This indicates that while a DNN is proved to be PAC robust by Provero, adversarial inputs can be still rather easily found within the verified bound. In contrast, DPAC estimates the maximum robustness radius more accurately, which falls in between the results from Iran and PGD mostly. Since the range between the estimation of Iran and PGD contains the exact maximum robustness radius, we conclude that DPAC is a more accurate tool than Provero to analyze local robustness of DNNs. Other than the maximum robustness radius for a fixed input, the overall robustness of a DNN, subject to some radius value, can be denoted by the rate of the inputs being robust in a dataset, called the robustness rate. We estimate the 4 tools of 100 images on 3 CFR10 CNNs. Provero results in a robustness rate that is even higher than the upper bound estimation from the PGD attack. And its robustness rate estimation hardly changes when the robustness radius increases. Iran is too conservative as the estimation quickly becomes unusable as the radius increases. The results of DPAC fall safely into the range bounded by Iran and PGD. So, compared to PGD, DPAC is more trustworthy with a probabilistic guarantee. Compared to Iran, DPAC is a more practical tool that can give meaningful results on a larger radius. Compared to Provero, the estimation given by DPAC is more faithful. We also run DPAC on larger datasets and networks. We test on CFR10 ResNets with different parameter settings. We found that the results are relatively stable and DPAC shows good tolerance to parameters. The ImageNet experiment shows our framework is efficient and scalable. We also calculate the Pearson correlation coefficient between the maximum robustness radius estimation and the Deep Genie index. Deep Genie is a testing prioritizing metric that measures the confidence of a DNN prediction on the corresponding input. We found that all 3 tools are highly correlated to the Deep Genie index. DPAC is especially more correlated on the robust networks, marked with a star. This suggests we use such metrics to prioritize the inputs to find unrobust cases earlier. In this paper, we propose DPAC, a method based on model learning to analyze the PAC-Model robustness of DNNs in a local region. With the scenario optimization technique, we learn a PAC model which approximates the DNN within a uniformly bounded margin with a PAC guarantee. With the learned PAC model, we can verify PAC model robustness properties under specified confidence and error rate. In future work, we want to improve our framework in multiple aspects, considering more complex input regions, stronger surrogate model templates, and extending DPAC to other properties. For more details and results, please refer to our XC paper. We are looking forward to your kind response and are ready for your questions at the virtual conference. Thank you.